Black holes are the most powerful and extreme things in the universe, and they're wildly weird and complicated. What would happen if you fell inside one, and what are they really? First, we need to talk about space and time. Space and time are the grand stage where the play of the universe unfolds. But space isn't a fixed stage, and time doesn't tick the same for everyone everywhere. In short, they're relative. Matter bends space, and bent space tells matter how to move. Put some stars and planets on the stage, and it sags underneath them. That misshapen stage, with all its little warps and dips, gives us gravity. Black holes do not just bend the stage, they're like trapdoors. Places with so much mass that the universe formed a no-go zone where the rules change. Most black holes form when very massive stars die. We explained this process in detail in our neutron star video. All you need to know now is that in the final moments of really massive stars, their insides implode at nearly a quarter of the speed of light. This packs so much mass so close together, creating something so dense that it sort of breaks the stage of the universe. A black hole with 10 times the mass of the Sun would be barely 60 kilometers across. If you look directly at a black hole, it looks like nothing. The space under their control is blocked by an invisible, one-way border called the event horizon. The event horizon forms a shell around a region of space that, once entered, is shielded from the rest of the universe forever. Because the black hole trapdoor deforms space so much, not even light can escape it. And with nothing escaping to transfer information from the inside, it's impossible to tell what it really looks like. We can still observe black holes because of their effect on matter. Things can orbit black holes just as they can orbit the Sun or a planet. Many black holes have disks of matter orbiting outside the event horizon. This matter can become incredibly hot, as close orbits can speed this matter up to half the speed of light, and tiny amounts of friction and collisions between particles heat them to 1 billion degrees, making the space around these black holes, ironically, incredibly bright. What would happen if you were to try to get close or even inside a black hole? First of all, you'd see the strangest funhouse mirror in the universe. Matter isn't the only thing orbiting a black hole. Gravity is so strong near them that light can orbit too. If you hovered just outside the event horizon, at the photon sphere, in any direction, you just see yourself. Straight ahead would be the back of your own head, as light from your back travels around the black hole to your eyes. Gravity also alters the passage of time itself. The stronger the gravity, the slower time passes. While you watch the universe above you speed up, those far away will watch you in slow motion. If you chose to fly away from the black hole, you might find that eons have passed for the rest of the universe, a freakish one-way time travel trip to the future where your loved ones are long dead. But getting close to a black hole can be incredibly dangerous. A painful death by spaghettification awaits you. Because your feet are closer to the black hole than your head, they feel a stronger pull of gravity, enough to pull you apart. As you descend, it gets worse. The pulling gets stronger, your body squeezed thinner and straighter, until you've been reduced to a thin stream of hot plasma, gobbled up in one final slurp, never to be seen again. Spaghettification is only a risk with smaller black holes, since they have much smaller radii. If you go to the center of a galaxy and find a supermassive black hole, you might be able to experience crossing the event horizon. As you approach the event horizon, a distant observer would think they never saw you enter it, seeing you stop and fade. The last light you emit, trickling up and out, away from the event horizon. Meanwhile, from your perspective, the void of the black hole rises up to meet you as light from fewer directions can reach you. The blackness envelops you until your only view of the universe you left is a tiny spot of light. Here, inside the event horizon, space and time are so horribly broken that real time travel is possible, so it's probably a good thing that nothing gets out. If anything could escape, it could create all sorts of time travel paradoxes and issues that break the universe. As scary as the event horizon is, it keeps us safe from that drama. Whether you have survived this long doesn't really matter, as now there's only the certainty of crushing death in your near future. Inside the event horizon, space-time itself is so bent and warped that whatever direction you move here, every forward you go leads only towards the center of the black hole. Trying to go in any direction only brings you to the center faster. To survive the longest, you must do nothing. In the center of the black hole, we find the singularity, a single point with all the matter that has ever crossed the event horizon, all crushed to a point infinitely small. There is no memory of the things that made it, as stuff disappears down the black hole trapdoor forever. The singularity makes all things equal. This actually breaks the universe in really cool ways. We've made a video about this problem if you want to learn more. But in a nutshell, everything that comes too close becomes black hole matter concentrated at the singularity. This lack of a memory of its past means that a black hole has only three properties: its mass, spin, and electric charge. Everything else is lost. They're a lot like fundamental particles in that respect. This actually means that every single black hole in the universe is the same. Sure, their mass is different and some spin faster than others, but if we were to put all the singularities into a magical physics museum, they'd be identical, like electrons. But just like fundamental particles, the properties of singularities are the best ways we can describe them on paper, rather than an accurate representation of reality. Our current theories about the universe, namely general relativity, are just not able to describe or explain them. The curvature of space becomes infinite, density becomes infinite, and our rules just don't make sense. The singularity has no surface or size, something like a divide by zero error in the universe. So singularities might not even exist, or be completely different things. But this is all we know right now from the best prediction we have from our best current theory of space-time. Also, basically everything you've ever heard about black holes, even in this video, is about theoretical black holes that aren't spinning because their maths is so much easier. But since black holes were born from dying stars that were spinning extremely quickly in their final moments, as far as we know, all black holes in the universe should be spinning right now. At incredible speeds too, up to 90% of the speed of light. This means that in reality, black holes are even more screwed up than they usually get credit for. The singularities of rotating black holes are even wilder. The rotation causes them to swell outwards into a sort of ringularity. This rotation is so powerful that space itself is dragged along. This creates another region around spinning black holes called the ergosphere, where it's impossible to stay still no matter how hard you try. Like a rushing whirlpool of space-time, the tide is irresistible, and the black hole makes you orbit it whether you want to or not. Okay, so what will happen to black holes as the universe ages and dies around them? Again, we don't know, but we have some ideas based on our current understanding of physics. Hawking radiation. In quantum field theory, the vacuum of space is boiling with quantum fluctuations. These fluctuations are creating matter and antimatter pairs of particles from nothing which only exist for a very short time before annihilating. When this happens near the event horizon of a black hole, one of these particles can fall in, stopping them from annihilating. The escaping particle is Hawking radiation. Ultimately, the mass of this particle must come from the black hole, so over eons, black holes will shrink and radiate away. Hawking radiation is not the stuff that fell into the black hole, it's new stuff, stealing mass from it. As the black hole shrinks, the Hawking radiation gets stronger, faster and faster, until what's left eventually evaporates in a flash of high-energy radiation like a nuclear bomb. And then, nothing. But that won't happen for a long time. A black hole with the mass of our Sun has a lifetime of 10 to the power of 67 years, which means that it would take 10,000 billion years to lose 0.00000001% of its mass. But most black holes are way more massive than our Sun. The most massive supermassive black holes in the centers of galaxies have lifetimes of 10 to the power of 100 years. How long is that? Imagine an hourglass filled with 1 grain of sand for every single particle in the universe. Every 10 billion years, 1 single grain of sand falls to the bottom. If we waited for all the sand to fall down, not even 1% of the lifetimes of these black holes would have passed. There is no good concept to help our brains grasp these timescales. Will we ever truly understand black holes? Really know what's going on inside them? No one knows. We can only see their outsides, and the theories we have probably get their insides wrong. But it's okay to not know everything. It just means there's still work to be done. It means there are still mysteries to solve and big ideas to think about, which is why humans do science. In the end, we can at least be sure that we still have plenty of time left to think about them before the last one melts away.